Hi, welcome to this lesson on trigonometry, trig identities part 2. Let's have a look at question 3. We want to prove the following identity and then state any restrictions if there are any. So on the left hand side I have a sine theta term that's being cubed, so sine theta times itself 3 times. On the right hand side I have a fraction, 3 sine theta minus sine 3 theta all over 4. So in terms of restrictions, there's nothing restrictive on the left hand side for sine because theta can be any angle. And the same thing for the right hand side. Theta can be any angle for sine theta and sine 3 theta, because when you divide by 4, it's fine. There's nothing restrictive going on. If there was some division by 0, then we would have restrictions. So there are no restrictions. Okay, so let's start off with the proof. Now, I'm going to use the right hand side because that has a fraction and it has a compound angle here. So hopefully once I've expanded that and simplified it, algebraically we can end up with a sine cubed term. So it's going to be 3 sine theta minus sine 3 theta. Okay, so the entire angle is 3 theta divided by 4. That's going to be 3 sine theta minus. Now, I can rewrite this as sine of 2 theta plus theta. Okay, all over 4. And the reason I'm going to do that is because if I expand this out using compound angles, I'm just going to be left with a simple theta and a 2 theta, which we can also simplify using double angle. So this is 3 sine theta minus. Now, so this is angle A, angle B. So you have sine of A plus B. So it's sine 2 theta cos theta. And because the sine is plus in the middle, it's plus again. Cos 2 theta sine theta. So that's the compound angle formulae for sine. All right, so now what I'm going to do is I'm going to expand that negative out. So that's 3 sine theta minus sine 2 theta cos theta minus cos 2 theta sine theta all over 4. So there's a lot of sine and cosine terms right now in the numerator. And our goal is to get it to look like the left-hand side, which only has sine. So what I'm going to do is anything that is not sine right now, I'm going to try and make it so that it's only sine. So let's carry on simplifying. So in the numerator I have 3 sine theta. Now, sine 2 theta we can break up. Okay, so sine 2 theta, or sine 2a, remember, is going to be 2 sine a cos a. That is your double angle identities. And then cos 2a, and there were 3 variations. There was a cos squared a minus a sine squared a. There was a 2 cos squared a minus 1, and a 1 minus 2 sine squared a. So we'll have to pick which one's going to be the most appropriate out of those 3 when we simplify this term. Okay, so sine 2 theta I can replace with 2 sine theta cos theta times that cos theta on the outside over there minus so let's think about this now. When we expand this term, there's going to be a cos squared theta term here. So maybe let's replace this cos 2 theta that'll also have a cos squared theta term, so maybe we can pull it out as a common term. All right. So that might be able to help us. So I'm going to choose this middle one here because that's got a cos squared only. Okay, so I'm going to say cos 2 theta is the same as 2 cos squared theta minus 1. And then that's also being multiplied by sine theta on the outside, all divided by 4. So again, lots of algebraic gymnastics going on here. We just got to make sure at each single step we are performing the algebraic steps correctly. Okay, so we have 3 sine theta. So now it's going to be minus 2 times sine theta times cos squared theta. Okay. And then I've got to be careful here because there's still a minus here. So it's negative 2 cos squared theta times positive sine theta. So that's negative 2 cos squared theta sine theta. And then it's going to be negative 1 times that negative 1, which is positive 1, times sine theta. So it's positive sine theta. All over 4. Okay, it's looking promising now because look at this. 3 sine theta plus 1 sine theta, that's 4 sine theta. Negative 2 amounts of sine theta cos squared theta minus 2 cos squared theta sine theta. So these are exactly the same term. So there are negative 4 of them. Sine theta cos squared theta, all over 4. Okay, getting there, we can pull out a common factor of 4 in the numerator. So we have sine theta minus sine theta cos squared theta, all over 4. So because everything is being multiplied now, I can divide those 4s into each other. So I'm left with sine theta minus sine theta cos squared theta. Now I've got a sine theta that's common to both terms, so I can pull that out as a common factor. So sine theta times 1 gives me sine theta minus, and then cos squared theta here, because when I multiply that out, I get sine theta cos squared theta. Lastly, 1 minus cos squared theta, that's a famous trig identity. That becomes sine squared theta. So that becomes sine squared theta here. So sine theta times sine squared theta, that is sine cubed theta. And that's exactly the left-hand side. So we've successfully proven that the right-hand side is equal to the left-hand side, and therefore have proven this trigonometric identity. So the main thing here was that we were able to perform the relevant trigonometric identities, such as the compound angle formulae, the double angle formulae, noticing special identities like 1 minus cos squared theta, and then using our algebraic toolkit, piecing that information together each step. Always go the extra mile and show each step. You might think you might save some time by doing it in your head mentally or just quickly scribbling it down. I say rather write out each step and analyze each step, because if you go wrong and you can't somehow prove it, you can always backtrack each step and see, where could I have made a mistake? All right, so that's how we would do this type of question. I'll see you in the next one.